We'll get to that more on that later. So let's talk about the sun. The sun is powered by fusion, and that's kind of what makes it really hot. So what is fusion? Well, you may have heard of fusion food before. It's kind of the same thing. Fusion food means combining two different types of food together, but for nuclear fusion, it's combining two different types of atoms, or two of the same atom, actually. It really doesn't matter, just combining atoms. So in this case, protons and neutrons, you can see down here, neutron, proton, 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 neutron, combining them to make a new element. That's fusion. Now, usually fusion releases energy. I'll go over more later where it doesn't release energy and actually takes energy to fuse things together. But for small atoms like hydrogen in our sun, yeah, it's a good thing the fusion releases energy, or else our sun wouldn't shine at all. Now, here's the thing. You may have heard of fusion energy before if you ever keep up on like future tech. The reason it's really hard to have fusion is you need really, really, really high temperatures. And not only do you need really, really high temperatures, you need those high temperatures with atoms that are really, really close together, or else they'll never run into each other to fuse. And so, you've probably heard of fusion is only 20 or 30 years away. Well, the problem is, at really, really high temperatures, it likes to melt everything we put fusion in. Uh, when we say really high temperatures, every single object would melt, vaporize, and turn into a plasma at the temperatures of fusion. So atoms themselves, the electrons are ripped apart. There's no metal container that can hold fusion. It doesn't work that way. So let's talk about fusion in our sun. So when I say really, really hot, 9 million Celsius is the minimum for hydrogen fusion. Our sun is actually at about 15 million Celsius, so it's even hotter than the minimum. You take 4 hydrogens, you slam them together, a few things happen, and you get a helium and some energy. That's fusion. That's the most basic fusion example I can give for hydrogen fusion. Now it's a little bit more complicated than that. Some electrons are released and you get like neutrons coming in. But in the most basic sense, you need 4 hydrogens to make 1 helium because you have 4 spheres to make 4 spheres, right? Now, one day our sun will become a red giant. And when it becomes a red giant, yes, it'll get bigger and swallow the Earth, but it'll also get hotter. And at the point of 100 million Celsius, it'll get hot enough to actually take these leftover heliums right here, because right now helium just sits in the sun and does nothing. When it becomes a red giant, it'll take those heliums and it'll take 3 of them together and form a carbon. And so 2 heliums combine to form a beryllium, gets hit by another helium, and you get carbon. And that will release even more energy. So it'll give our sun another 100 million to 200 million extra years in its life, burning helium instead of hydrogen. Now, as you can see, it only goes up to about 200 million Celsius, so there is more beyond 200 million. We'll go more on that later. So our sun isn't the hottest one out there, no. But it'll get hotter. It still won't be the hottest thing out there either, but it will get hotter over time. In fact, it gets 1% hotter every 0.1 billion years. So every 10 or every billion years, it gets 10% hotter. Now, going on from that, a little bit more about fusion. So fusion in stars can go all the way up to iron and nickel. So if you've seen a periodic table, iron and nickel are pretty near the top, right in the middle. They're not the biggest elements. They're 26 and 27. So what about all the rest of the stuff like gold, uranium, silver, platinum, the valuable stuff? Well, the reason it's valuable because it's rare, right? Gold is rare because stars can't really make it unless they go supernova. So for fusion, it's stuck at 1 through 26. Really, actually, fusion only starts at helium 2 through 26. So our sun will stop at carbon dioxide, oxygen, but bigger suns can go even bigger than that. Now, you might be thinking, or if you've already taken the quiz, there's a question on there, where does the sun get its energy from? Well, the sun gets its energy from mass. When you take hydrogen, let's say you start out with a kilogram of hydrogen and fused it into helium, you would not end up with a kilogram of helium when you're done. You would end up with 0.993 kilograms of helium. So 0.007 kilograms are gone. That's called the mass defect. It's literally, boom, energy. Now, you've probably seen this equation before. If you were here for the last live session, I went over it with fission, but the same applies for fusion. The mass, that 0.007 of helium that's no longer there, times the speed of light, which is 300 million squared, equals how much energy is released. And it's a lot of energy. A lot of energy. Oh, and I should mention in this example, 1 kilogram loses 0.007. Well, the sun loses about 1 trillion kilograms every day. So it's a lot of mass is disappearing as well. Now, when I mention how much energy, let's take a look at what that looks like. So nuclear fusion for one atom of helium that's created, 17.6 mega electron volts of energy released. But you probably don't know what a mega electron volt looks like. Okay, so let's say you have a gram of hydrogen. And a gram, for comparison, is about a paper clip. Or if you're dealing with pretzels, it's about half a pretzel. If you have chocolate chips, it's about one chocolate chip or one Skittle is a gram. So it releases, if you were to fuse 1 gram of hydrogen, it releases 280 billion joules of energy. Because people seem a little bit confused. It should kind of make sense because if I go back and look, a helium is made of 4 things in its nucleus, 2 protons, 2 neutrons, right? Well, to get 4 things in your nucleus, you're probably going to need 4 things to start out with, 4 protons. So yeah, 4 hydrogens to make 1 helium. Now, the process is a little bit more complicated than that. Like if I go back here, yeah, you start out with a deuterium and a tritium and they have to run into each other, but the extra neutron goes flying away anyway. So yeah, you need 4 hydrogens. So we're going to start talking about the sun and stars. That's our next unit. Now, I want to tell you that fusion only happens when it's really, really hot. And the sun is not the same temperature everywhere. No star is, right? Core of the sun is only about, well, really, the core where hydrogen fusion happens is only about 3% the size of the sun. So this blue circle right here is actually too big. This inner blue circle is pretty much only place where fusion would be happening, that tiny little part of the sun. And the reason is, well, one, it's 15 million Kelvin. You can see right there, right? You need a minimum of 9 million Kelvin. But two, look at its density, 150 grams per cubic centimeter. It's about 150 times more dense than water. So you need the hydrogens packed really close together to actually cause them to run into each other. If you look at like the outside of the sun, like the surface of the sun, 5,800 Kelvin, that's not very hot. The core of the Earth is about the same temperature. And look at that density. That's 10 with 7 zeros in front of it. 0.0000001 is not dense enough to cause fusion to happen. That's not even dense enough to breathe in, okay? So right now, the only place the fusion is happening is in the core. And that's actually the same for all stars. So what about a bigger star than our sun? Well, they have different layers of core. So the inner is obviously the hottest, and as you get farther out, it gets colder. So we know that hydrogen fusion happens at about 9 million Celsius. Helium fusion happens at about 100 million Celsius, up to 200 million. And then as you get farther down in the star, it can fuse heavier and heavier elements. So oxygen formed at 600 million. Down here at silicon, it fuses at 2.7 billion, up to 3 billion. So as the star gets hotter on the inside, you can fuse heavier and heavier stuff up to iron. But then it's done. It can't go beyond iron because iron actually takes energy to fuse.